So there's an AF16 individual, and here we have an HK104 individual. And so I'm representing, say, chromosome 1 and chromosome 2. They're different sizes. They have more than 2 chromosomes. But so we know that this individual is diploids. They've got 2 copies of chromosome 1, 2 copies of chromosome 2. And we know that this worm is healthy. And despite the fact that on its chromosome, at this locus, this place where we're doing the PCR, it only has AF16 sizes of the chromosome. But if you look in, let me see, now let me erase the HK104 worm with a bigger eraser. So if we look in one of those F2 grandchildren, that's close enough. This is what its chromosomes will look like. Part of chromosome 1 will be from AF16. Part of those chromosomes will be from HK104 because it's a grandchild. So it's a genetic hybrid. It's got a combination of the blue from AF16 and the red from HK104. Sorry, opposite. Red from AF16, blue from HK104. And the same will be true on other chromosomes as well. So we might have a chromosome 1 that looks like it's shown on the bottom, and this looks like chromosome 2. So this individual happens to be a delayed, let's say, diseased D, F2. Yet it has the same genotype as its AF16 grandparent. It's got 2 copies of AF16 chromosomes in the same spot on the same chromosome, chromosome 1.
Okay.
And so that's what that shows. There's one band is the AF16 sized band. In the F2 delayed worms, they've got the exact same genotype. All of their copies of the chromosome are the AF16 size.
Right.
So your question basically at this point was, if these individuals, the AF16 grandparents and their diseased, delayed F2 grandkids have the same genotype here, how is there a phenotypic difference? How are these worms healthy and these worms sick?
Right.
So what I'm saying is the difference is probably not here on chromosome 1. The difference might be that it's because these are grandkids and they're hybrids. So it might be that the combination of having red AF16 chromosomes here and blue or HK104 chromosomes somewhere else, which we're not looking at because we're only doing PCR asking about this one spot in the genome.
Right.
So that's all the information we have. So what Leo and others in the lab continue to do then is to ask, now that we think you have to be red over red, AF16 over AF16, both copies of the AF16 chromosome here, now we're looking everywhere else in the genome to figure out where is there a difference genetically between what AF16 has and what the delayed worms have.
Okay.
In other words, it's clear that being red, having all red chromosomes is not a problem because AF16 worms are fine. They're healthy, they make babies, they're fine. So it must be that there's a specific combination of being red at one point in your genome, so say that's one gene. You get the AF16 version of that gene, but you get the HK104 version of a different gene. Somehow, when you combine the red version of one gene and the blue version, the HK104 version of a different gene in the same organism, it doesn't function properly anymore. That's the story.
So if you do 2 AF16s and look at their grandkids, they don't have that problem?
Exactly.
Okay.
Perfect.
So then it couldn't just be this section repeating itself. That's why. Okay.
Right. And so I apologize for having glossed over this in class.
No.
And I should have spent more time doing it. But that's why I tried, at least vocally when I said it, to underscore the fact that it's only in hybrids.
Okay.
So that's when I said the word hybrid, what I should have done was spent the time I just spent telling you about what it means to be genetically hybrid.
Okay.
So it's only in the hybrids that we see disease, developmental delay. And it's because this random, or mostly random, combination of different genomes, the AF16 and the HQ104 genomes, coming together in the same individual.
Okay.
So you can think about this also kind of like the horse mated with a donkey produces a
Right.
mule, and the mule is sterile, which tells us that there's genes coming from the horse and the donkey, the two parents, that don't function properly together in the mule, their offspring, and that causes them to be sterile.
Okay.
So this is exactly the same thing. We're trying to figure out what are the genes from AF16, one point on one chromosome here, and what is the other gene, the gene that comes from HK104, presumably here, that when you bring them together in a hybrid, one of their kids or grandkids or great-grandkids, causes those hybrids only to get a disease.
Okay. Okay. Sounds good. Thank you so much, Dr. Ross.
You're welcome.
Bye. Have a good day.